Hi, everyone. Thank you for being here with us. We're going to give it a minute or two as we're admitting people from the waiting room. So just bear with us for a minute or two and then we'll get started. All right, well, we're going to get started. Thank you all for being here and for joining us to the Washington University Climate Change Program Speaker Series. I'm Beth Martin, the director of our Climate Change Program and a teaching professor in environmental studies. And so I'm excited to be here tonight and excited that you're here to join us. I'd like to thank the McKelvey School of Engineering and the Global Health Center at Washington University's Institute for Global Health for partnering with us to host Dr. Shindell tonight. First, I'd like to give you a couple of, which everybody probably knows, but we'll go over them anyway, some Zoom meeting functions. This is being done in a Zoom meeting and our speakers will be spotlighted. So please keep your sound muted during the presentation. You can keep your videos off as well. Questions to the panelists will be posed through the chat. And there may be an opportunity, and you know, if you're interested in asking a question live as well. But if you can indicate your interest in placing your question in the chat, that will help our moderation. If you choose speaker view, because we're spotlighting our speakers, if you choose speaker view on the top right-hand corner of the screen, you'll be able to see our moderator and our speaker on the screen. So I'd like to introduce our moderator tonight, Professor Randall Martin. Professor Martin is the Raymond R. Tucker Distinguished Professor in the Department of Energy, Environmental, and Chemical Engineering here at Washington University. His research focuses on characterizing atmospheric composition to inform effective policies surrounding major environmental, public health challenges, from air quality to climate change. Randall also serves on our Climate Change Program Steering Committee. Randall, thank you so much for being with us and for moderating tonight. I'm now going to turn it over to you.
Thank you, Beth. And it's truly an honor to introduce today Dr. Drew Shindell, the Nicholas Distinguished Professor of Earth Science at Duke University. As an expert on climate science and policy, Dr. Shindell has testified on these issues before both houses of the US Congress and at the request of both parties. He has co-led chapters of the Intergovernmental Panel on Climate Change's 2013 and 2018 reports, and is chair of the forthcoming UNEP Global Methane Assessment, and chairs the Scientific Advisory Panel to the Climate and Clean Air Coalition. He has been named one of the top 50 scientists by Scientific American. He has received numerous other awards, including being named a Fellow of the American Geophysical Union and of the American Academy of Arts and Sciences. It is an honor to host his presentation today. Professor Shindell, the microphone is yours at your convenience.
Thank you, Randall. It's a pleasure to be here and I appreciate the invitation. I'm going to do my best to share my screen with you now and find the right window. I think I've got it. Hopefully you can see this. And what I want to do really is talk to you about impacts of global change on, I also like to make my little, there we go. People coming and joining are still welcome, but they're putting little messages on my screen. So just getting rid of those. Impacts of global climate change mitigation on health, labor, and crops in the United States. And of course, we're focusing on the United States, but I'll try to draw a few impacts here about other parts of the world as well. And really the kind of work would not be possible without colleagues from my former institute, NASA Goddard Institute for Space Studies, which develops one of the climate models, climate and composition models that a lot of this work is based on, but also a large group at Duke. And you can see that the majority of the people named there are Duke students. And so I really want to call out that my research group has been instrumental to any of the work that I'm going to show here. So So before I show you any of the results, I want to kind of set the stage by talking about the kind of questions and motivation for this work of looking at the impacts of climate change mitigation in the United States. And one of the things that we hear a lot is the cost of inaction on climate is far greater than the cost of action. This has kind of become fairly accepted wisdom in the community and even in the general public, in particular since a very influential report from the UK government, the UK Treasury Commission, Nicholas Stern to lead a report on this. And this is the kind of thing that I think we, in principle, believe to be true. We use this to try to justify climate action, but in practice, there's some issues here that make it hard sometimes to convince people. And one of the things that we see is that here's an example from the OECD, the Organization for Economic Cooperation and Development, essentially all the wealthy countries of the world. And what this is showing here, the economic consequences of climate change. You see the regional damage as a function of GDP. And you see that this was issued in 2015, so there's nothing, it's relative to the start of that period or relative to about 2012 or 13 when they began looking at this. And you can see places like OECD America, so that's the US and Canada, OECD Pacific, Europe. You're out here in maybe around the middle of the century when you start to see a few tenths of a percentage point of GDP lost from climate. In other parts of the world, some places it's a higher percentage of GDP. But really the basic point here is that it takes quite some time for the damages to build relative to where they are. Climate is a very slow moving problem, as I think we all know. I like this image from the OECD webpage, not only because it's showing the regional damages, but because the next heading you can see down there in the lower left, right, is exactly the same motivational message. Doing nothing will cost more than acting. But then you look at this picture and you think, doing something means taking action now, and it means spending a lot of money to transform the economy in the next decade or two. And what it's saving me is all these expenses, which are very, very distant in the future. So yes, in the long run, doing nothing will cost more than acting, but in the short run, acting will be expensive and it will cost far more than the benefits that we expect to get through reduced climate change. So this kind of brings me to another common question, which is really, how do we value long-term changes? And there, we have kind of psychological ways of thinking about it. We have very formalized economic ways of thinking about it as well. The short answer is that we don't value long-term changes all that much. If you look at, say, a typical economic discount rate used in most of the literature, we might say value of money declines by about 3% per year. So if something is causing us, say, $1,000 worth of damage in 100 years, that is worth about $50 today. Right? That's giving us a sense of how we don't tend to value things that are taking place in the far future. Now, under the Trump administration, they raised the rules, or they changed the rules to change that value quite a lot, so that $1,000 in the future was worth roughly $1 today. So they really, really dismissed the value of long-term changes and long-term damages. The new administration has gone back to the older one, but even with the older one, right, $50 of value assigned to something that's $1,000 in the far future, it really means it's not really considered all that important right now. This is a contentious topic, but it's one that I'll kind of try to return to. What we've been trying to deal with is this issue that this is essentially a chart that's exactly from the last IPCC report, but I've simplified it. That's the adaptation. It's cut out a couple scenarios that were not really relevant here. And what it shows is at the time, this report was written in 2013, the scenarios kind of diverged from one another around 2010. And what it shows here is in blue, there's a scenario that gets you to around 2 degrees, what we've all pledged for. There's one that's more like 3, a little over 3, more like around 5. And what you see is that, they all start to diverge in 2010, and in 2020, well, you can't really tell them apart. And in 2030, you can't really tell them apart still. And by 2040, this high one is starting to separate from the other 3, but you still can't really tell those apart very well. And maybe by around 2050, you can start to see some separation between the low warming scenarios and, say, the moderate and the high scenarios. But the point is that it really does take a long time to change, to have a noticeable impact on climate change by taking action now. And so people are not wrong when they say, hey, you're asking me to do all this stuff now and I won't see the benefits from that for a long time. That is actually, an unfortunate truth that it takes a long time for climate to respond to changes, say, in our CO2 emissions. So what we've been trying to work on over the past few years in my research group is examine several of the impacts of climate policies, right? So transitioning to a low emission economy and way of life in some cases. And we're examining impacts that we feel we can reliably quantify, put a value on, and see how they unfold over space and time. And so we're looking at impacts. Our primary interests are human health, their labor productivity, and their crops, agricultural yield of some major crops. And what I think is different than some of the work, like the OECD work that I just showed you, was they're only looking at damages due to climate change, whereas we are focused on the impact on health or labor or crops. And we don't really discriminate based on how they are affected. If they're affected by air pollution, that's important. If they're affected by climate, that's important too. If we knew how to quantify other things, we would include that too. But we're really trying to focus on these endpoints and not pay so much attention to the physical pathway. What we've done, and this is kind of something much more for those who are really immersed in this area of research, so that don't really worry about the details unless you're kind of a specialist in this area. But this is the model that we use. I mentioned the NASA Goddard Institute for Space Studies model. It's the latest version being used to support the next IPCC assessment. And one of the things that's nice about that is we have simulations from the current generation of scenarios, which are called SSPs, short for Shared Socioeconomic Pathways. And so we have lots of different simulations looking at different possible futures, those that are consistent with, say, the Paris Agreement versus those that are moderate and those that are more like reference case, sort of business as usual. We have done some work to run and get high spatial resolution for, not for climate, but for particulate matter, PM 2.5. So it's fine particulate matter, smaller than 2.5 microns, which is narrower than I can actually pinch with my fingers. But the kind of thing that when you inhale can get really deep into the lungs and cause serious health problems or even death. And we've also saved some extra data that's not part of the standard output with hourly surface temperatures, and that's particularly important for labor. And if you're working, say, out in construction and you're hammering the roof on a house, it's pretty hard to get out of the heat. And all you can do is shift the time of day, but you can't avoid it by, say, air conditioning a house that's not built yet. So those are the kind of things we wanted to have the data from this model of composition and climate that allow us to calculate the impacts on health, labor, and agriculture that we're interested in. We also needed hourly ozone, for example, to do the agricultural impacts. We did a couple, which I'm not going to focus on today, but what I do want to include these scenarios to make one important point that I'll return to. And we did some simulations really just focusing on energy sector decarbonization And that's one of the biggest parts of a transition to a low warming planet. But the main reason I wanted to talk about these is because we ran these to look at the effect of this transition around the world, like all of these other shared socioeconomic pathways done by the research community around the world to support the IPCC. But we also did those looking at the transition just in the US, and that allows us to tease apart, how much of the impact is due to our actions versus others. So I want to show you a couple things here about the emissions and concentrations that drive the scenarios. So there's too many to go into all of these in great detail, but for those who are familiar with climate, I want to start here on the legend and introduce these a little bit. The number before the underscore is the shared socioeconomic pathway. And I'm not going to really go into that as it's not particularly relevant to what I want to talk about today. But the number afterwards is the radiative forcing, and that translates to roughly the temperature that these scenarios will achieve in around 2100. That would be something like about 3/4 of the number here. So this 1.9 watts per meter squared is a 1.5 degree scenario. So that's the aspirational goal of the Paris Climate Agreement. This 2.6 is a 2-degree scenario. And then you just get higher and higher, right? At 3.4, 4.5, 6, 7, and 8.5. And these last two will be my reference case. And I will primarily compare with this 7.0 watts per meter squared or 8.5, which are two versions of kind of, if we don't really change from our current trajectory and what we've been doing in the recent past. So if we start on the left here, under these shared socioeconomic pathways, the nitrogen oxide emissions in the United States, which is a precursor of both ozone and particulate matter, right? There's a huge spread in what they might do. I've lost my cursor briefly, there we are. They might go up under the 8.5 reference scenario, the warmest one. They might kind of stay fairly level and decrease slowly under the 7.0 reference scenario, or under a very aggressive one, like the 2-degree here in orange or the 1.5 degree here in red. They might drop very, very greatly and very, very quickly. We don't have, a clear image in our minds because we haven't made the socioeconomic decisions yet that would allow us to foretell which one of these is most likely. Under the decarbonization scenarios, you can see first there's an oddity that we start from a different point, and that's because we are not using the same emission scenario, the same emission database rather, as was provided to the community to use for all of the other simulations. And this one has more emissions from the United States at the starting point. And we think that actually that might be more realistic. But the interesting thing here is, you under the reference case developed by a European research group here is what we're using. The emissions decline under their reference case. They decline more when we decarbonize, but naturally there's not much difference between the orange and the blue, which are energy sector decarbonization globally or just in the US. Right? There's a huge difference over here if we turn to CO2, however, right? If we just decarbonize energy sector in the US, we pull down CO2 from this dark blue one to this light blue one, not very much. And of course, if the whole world decarbonizes, it makes obviously an enormous difference. So what we can see is that, as you'd expect for something short-lived like nitrogen oxides, which are a short-lived pollutant, we are going to have a huge effect on our own emissions are going to control our own policies are going to control our own emissions. When you look at a global pollutant like CO2, you see that what the US does is not going to have a great effect unless done in concert with the rest of the world. And you also see that there's no chance of getting something like, our emissions here of nitrogen oxides fall by more than 50% within a decade under these aggressive scenarios. CO2 keeps going up even under the aggressive scenarios, right? Because again, it's a slow global pollutant. It takes a long time for it to move. For those particularly in Professor Martin's group, who are interested in surface particulate matter under using the SSPs. Our population weighted exposure in the United States is 7 micrograms per cubic meter. Under the energy scenarios, it's 8.9. And so that's the difference in this starting scenario. So that gives you some idea of the uncertainty. Depending on what we put into our model, we get a different amount of bad stuff people are breathing in. And then we tried to compare with some satellite-based estimates and an estimate produced by the US EPA fusing models with ground monitors. So we're kind of in the ballpark. We're even better, I think, with this higher emission. So mostly we focus on that one going forward. Here's what we see for results. So that's kind of the background of our simulations. Here are the results we get for premature deaths due to breathing elevated levels of PM 2.5, and that's shown there on the left. What we see is under a reference case, the number of people that die every year goes up rather than down. Under the moderate cases, it tends to decrease, but fairly slowly, something like this group here. And under the very aggressive cases, there are very, very strong declines in the total burden on public health. If we switch to the right for a second, here it's done in per capita. And we can see that the reason this orange one here, this 8.5 high reference emission case went up, is not because the air got more polluted. It just got slowly cleaner, and it got cleaner less rapidly than the population grew. So that the total burden, this is both a function of number of people and of population aging, which can make people more susceptible. And so the burden goes up over time, but the actual per capita goes down. And so that's if you normalize by the number of people. If we go back to the left again, one other thing you can see here, which is kind of interesting, is this scenario has high emissions and then lowers them. So it's kind of a delay scenario. And that leads to some interesting consequences too, which I'll return to in a moment. Those black bars, these vertical bars, I've only put them so it's a little easier to see on the reference scenario, the 7.0 reference scenario. So it's about a 5 to 6 degree warming. And that shows the uncertainty across our 5-member ensemble of simulations. So you can't really tell apart, say, this yellow one from this dark blue one or this gray one here, but you can certainly tell apart this group from, say, this lower group. And even this 1.9, you can tell apart this really most aggressive one from this pack of other less aggressive ones. Ozone is one of the other pollutants, and if you still manage to keep what I just showed in the back of your head a little bit, ozone, the deaths from that go up in the 8.5 as they did for PM. They also stay fairly high in the 7.0 reference case. And again, you can see very, very rapid drops. In this case, even more rapid. We could reduce about a third of the PM 2.5 deaths within a decade under very aggressive decarbonization. With ozone, we can reduce about 75%. The total magnitude is smaller. PM was around 200,000. Ozone is about 60,000. But you can make a bigger and faster dent there. One of the reasons for that is that there's the epidemiological evidence for ozone stops at kind of a relatively high exposure threshold. So that's why you also see over here in this red one, the 1.5 degree scenario, there's no real improvement after 2040 because most areas of the United States are already below the lowest level at which we have exposure measurements that correspond to adverse health impacts. It doesn't mean there aren't any at lower exposures. It means we don't have evidence for it. So that's kind of a peculiarity of the way ozone is set up rather than PM. And if we turn to the right again and look at per capita, we see that in this high scenario, we really don't manage to lower the level of ozone. And this is despite reducing lots of the precursors, like the NOx still goes down. One of the reasons is there's still a lot of natural gas used in that scenario and a lot of methane. And methane is an important ozone precursor, which tends to offset all of the other precursors that are reduced and keeps ozone at about the same level as a function of time. So we can make these big dents in deaths from ozone and particulate very, very quickly. What about heat? That's shown here. And there's several things that are different. First is the whole shape of the graph, right? We're starting from a point where the deaths today are not so large. They're only 20,000. Again, ozone was about 60 and particulate matter was about an order of magnitude higher than this, about 200,000. But in none of these, even the most aggressive ones, they don't go down, they go up. And it's a question of not whether they will go up, but how much, right? So the most aggressive scenario is this red one. And, it still more than doubles by 50 years out into the future, which is a lot better than this high one where it goes up by, a factor of 7 or something, but they're going up in any of these. The uncertainty range is this black bar again, is also much larger. So it becomes statistically almost impossible to see any difference except for the most extreme case for the first half of the century. And what I should stress is that these are actually enormous differences in infrastructure, right? This red one is the 1.5 degree scenario. And the blue one that's just a little bit above it, but statistically indistinguishable through 2060, that's the one where the bar is centered on. So it's this one. That one is business as usual. This one, the red one, phases out essentially all use of oil for motor vehicles. Before mid-century, it phases out all use of coal before 2040. Back here in the 2030s, coal is gone, oil is gone by the 2040s. There's some gas, whatever gas is used is fixed with carbon capture and storage or decommissioned by 2050. This is a huge transformation relative to the baseline, and yet you still can't see any statistical difference even at 2060. You can at 2070, they finally separate, but it takes 50 years, right? And that's that point again that I was making in the beginning and that we saw in, it's not a surprise, we saw this in the last IPCC assessment. Climate responds very slowly, even to very radical changes. What you can also see, and again, it's hard to show all of these on the same screen at once unless they're too small to read. But I talked about the magnitudes here at the beginning, 20,000 versus say 200,000 for PM. We can, under these low warming scenarios, we controlled PM so well that I don't really expect you to remember the values, but there was a sharp decline from that 200,000 so that we were down to say around 40,000 or so, which means heat becomes in the lowest warming scenarios comparable. And in some of the middle ones, heat can outpace and become a more important source of premature death than air pollution in the future. And so while it starts small and an inexorable rise that we see at least over the next 50 years or so means that it becomes very, very important. But again, in the long term. And so that goes to this question of how do we value near term versus long term. This is one that many of the graphs I just showed you are for a paper that's now submitted. This one didn't make it in the final paper, so I apologize. It changed the color scheme a little bit as we didn't perfect it. But what it shows you is something interesting too, which is this brown one. And that's the one that overshoots. And so there's a bit of a tricky thing here when we were working on the 1.5 degree report. The governments of the world, after agreeing to the Paris Accord, asked the IPCC to write a report and said, okay, tell us how we get to 1.5 degrees. And then we went off and said, what does that really mean? 1.5 degrees relative to when? And 1.5 degrees, like averaged over the whole planet? Or do we leave out the polar regions because we don't have data going very far back in time? And 1.5 degrees for a day or a year or a decade? Or can you go over 1.5 and then come back? And it's all very confusing. One of the most contentious was that last question, can you go over 1.5 and come back? And the consensus, largely because it was very hard to find scenarios that didn't do that, and still was to say that that was okay. What this shows is that a scenario that overshoots, right? It might come back to the same eventual warming. This one matches one of the others in 2100, which is a little off the edge of the scale here, but there's a real impact on what people are breathing over the next several decades on the way to that. Right? Essentially, you're not phasing out your coal-fired power plants quite as quickly as you would, and instead, you tend to do things like this. So you have coal-fired power plants, a lot more of those in the next 20, 30 years. And later in the century, you have loads of these. This is a biofuel energy with carbon capture. Well, this is just a biofuel energy plant, but in the models, they're biofuel energy with also burying the carbon. And so the plants, the trees suck up this carbon when they grow, you burn them for your power, but you bury the carbon, and these are a net negative source. And so they make up for all the CO2 from the coal-fired power plant. And so in the end, for climate, it's the same thing to build lots of renewable power as to run coal, emit tons and tons of CO2, but then take back that exact same number of tons in the future. Unfortunately, and what that previous graph just showed, is that's not the same for people, because people have to breathe all of the stuff that you can see in that upper left photo. There's stuff coming out of those coal-fired power plants in addition to CO2, which is invisible. There's plenty of visible stuff, and it's the same thing for motor vehicles and et cetera, et cetera. So the quicker you phase out fossil fuels, it might not have any difference if you, in the long run for climate, if you make up for CO2 with drawdown of CO2 in the far future, but it has a big difference for public health along the way. One of the things that we can see, and the reason I really wanted to emphasize some of these experiments looking at the US, is that when we look at air pollution, so we look at ozone here and the mortality from ozone, and see how that relates to our emissions of air pollution in the United States, very high correlation. Same thing for PM, and same thing for heat correlation with global CO2. But heat is not correlated, as you wouldn't expect, with US domestic emissions of air pollution. And domestic air pollution is not really correlated with global decarbonization, right? So you can have scenarios that decarbonize more or less quickly, but what other countries are doing for their fossil fuels, will have a big effect on our climate and therefore heat exposure, but have almost no effect on the quality of the air we breathe. And that's shown over here on the right, for example. Relationship of PM mortality, it's just not correlated at all with the overall CO2 concentration. Too many different possibilities for other parts of the world. But we are in control of what happens to the air we breathe. The correlation between ozone and PM and our own emissions is extremely high. And that was also visible there in some of the charts that I just showed. When you look at the energy decarbonization in the US, you could get the bulk of the changes that we saw from US action. When you looked at heat, you could only see that when the the entire planet took action. So I could go back to that if that wasn't clear at some point, but that's a real fundamental difference in these two. So they have a different evolution over time. They have a different source and control. One is a global, one is a local phenomenon, but they're both coming from the same kind of policies, right? Which is essentially phasing out fossil fuel use. One other thing we can do that I liked a lot from working with scenarios that were provided to the global community is compare our results with those of other models and try to figure out, is this just something our models get? Because maybe it's weird. Maybe it does something peculiar, right? So here's the difference between a 2°C scenario and what I'm calling the low reference case, the 7.0. And so you see over time here, the average PM over North America, remember it was around 7 or 8 micrograms, and it drops down by a little over around a half a microgram going forward in time under the 2C relative to the reference. It actually drops a little in the reference too, in at least our model. But here on the right, you see all the individual models. And that's the one thing that's quite interesting. The reference is this dark one. And you see that the models really don't agree all that well. And it's quite model dependent. 2 models have an increase in exposure under a reference case. 1 model shows almost nothing, and 3 have decreases. When you look at the 2 degree C scenario, so this is kind of the minimum from the Paris Agreement, they all have decreases, but they vary quite a lot. You know, this is a Japanese model, which has the highest value, almost a microgram. And then you compare that with, say, the NOAA's model, the US National Oceanographic and Atmospheric Administration. And, you know, it's almost a factor of 3 difference. By coincidence, then, they end up having fairly similar differences between the 2 scenarios. So the benefit of acting is more clear than what happens on either scenario, suggesting, you know, for example, this Japanese one, it's stronger in both cases, right? So there's systematic differences across these models, which are very large. Their response to policy, however, you know, it's pretty much about half a microgram per cubic meter for the average person. And that is fairly, still a substantial range, but it's fairly consistent. So I think that's really interesting to see that we can have a little more confidence in the benefits of policy than we can in the evolution of any particular possible future. I don't want to spend too much time on this because I want to return to it in a moment, but we can also look at labor. Work loss due to air pollution is what's shown here on the left. And you can see this is something like around 12 million days lost. This is pretty interesting in that air pollution affects essentially everybody. It's a little less if you work in, say, a filtered office or something, but pretty much everybody's going to be breathing in, at least on their way to work, or exposed in the night, in the day, and transit, and depending on their lifestyle at some point. Remember the work loss or the heat, the difference due to heat was very hard to distinguish from one scenario to another. We don't get any significant results prior to 2050 for differences between scenarios, but we get a growth from present day, and then we end up with something like 18 million in 2070 for the difference between essentially this one down here, this red one, and this blue one here. So heat, again, it's not important early on, but by the end of this, it's even more important than effect on labor than it is for air pollution. But again, it's going to be different people. And so I'll return to that in a moment. For agriculture, not only is the temporal evolution like it was for human health and for labor different for climate and for air pollution, but it can be even of the opposite sign, with climate giving you an increase so this is done in terms of yield losses. And so yield losses decrease when you reduce ozone, right? That's this dash line. Yield losses increase when you reduce CO2 because CO2 fertilizes plants. And so it's actually a kind of a perverse thing where you think, that shouldn't really actually to help my agriculture. But in the short term, it appears that it could, except that, you know, you would only get this kind of answer if you ignored air pollution, right? And the other thing about this is it becomes a little bit difficult to even define what's climate and what's air pollution, because CO2 could be thought of as air pollution, right? It's actually the chemical floating around in the air that the plant is exposed to, the same way ozone is, although typically people think of it, and past studies always use CO2 as part of climate. So this is the response overall to temperature, precipitation, and CO2. CO2 in the short term can help can help plants, but over the long term, the increase in temperature suppresses wheat yields, suppresses soy yields, drought increases losses, of wheat and soy. And so mitigating climate change is helpful to these crops in the long term, reduces yield loss. And again, you see that if you compare with the direct air pollution, ozone, air pollution is way more important in the short term, but towards the end of the scenarios, climate dominates. The one other thing I want to say now, I want to talk a little bit about the spatial pattern, since this has all been about the temporal pattern, right? Air pollution impacts are pretty much uniform in space. That is, if you breathe an extra 3-5 micrograms per cubic meter squared, whatever it is, it has the same effect on a person in New York as it does in Atlanta. But that's not the same for heat. And people very much acclimatized based on what they're used to. This is from one of our studies where we looked at how to incorporate this, and you can see these southern cities down here. When it gets to high temperatures, the risk of death goes up, but it doesn't go up nearly as much as it does in these colder cities, where people are just not used to dealing with the same kind of temperature that you might get in the southern cities. And so this geographically, we're going to have a very unique pattern on human health, and we're going to see in a moment that's also true for air pollution. So here's something we put together where the students again did most of the work here to help create a website where we have the ability to look at all of our different SSPs and different quantities. I'm going to play you a little video of me using this. You can select the SSP you want, you can select the year you want, you can select the quantity you want to look at. And so now we have deaths due to ozone on the left. California, for example, about 8,000 fewer deaths if we look at this 1.5 degree scenario than the reference. It was about the same for PM, but you see for Florida, ozone is more important, way more important. If we go to New York, ozone about 4,000, New York 8,000. So it's the other way around in New York and Florida. New York much more sensitive to particulate, Florida much more sensitive to ozone. If we look at deaths due to heat exposure, now we see if we put the cursor over California, it's about 2,000 fewer deaths per year, whereas again, ozone was about 8. So it's way more important. Air pollution never catches up. But in somewhere like Minnesota, right, because people are more sensitive in cooler climates, heat is more important than air pollution. Minnesota is also not very polluted. If we turn to labor now, right, this is lost work days due to air pollution, 2070 on the left. And now I'm going to find lost work days due to heat on the right. And the total is much higher for heat, but the distribution is really different. So New York, 700,000 days due to air pollution, whereas almost nothing due to heat. And that's, let me just pause for a second. The reason for that is because my example that I mentioned before, I was a construction worker, right? It's certain types of work are really affected, and it's the kind of work that you have to do outdoors and where it can't be air conditioned. And that's typically farm work, that's construction work, and that's transport and some kind of industry. And so that really affects the southern states where it's already warm, where you pass thresholds that are easy to deal with. So in New York, again, it was hundreds of thousands of lost work days due to air pollution and almost nothing due to temperature. In Texas, I just put the cursor over Texas on the left, and lost days due to air pollution are around 400,000. And now if I go over to the right and look at the lost days due to heat, wow, it's over 2 million, right? So depending on where you are, you will get much larger or smaller effects from air pollution or heat on labor and on public health. Right? Northerners are going to be much more sensitive to heat-related deaths, but Southerners are going to be much more sensitive to heat-related labor conditions because, you know, it's hard to work when it's really, really hot. There's only so much adaptation that's possible. So in summary, I would say the benefits to health, labor, and crops. I went through this pretty quickly. I hope it wasn't too quickly for people, but I would say that in the next 40 years, right, we saw benefits, reduced mortalities due to health. We saw benefits to labor productivity. We saw benefits to agriculture. And they're really almost all driven by air pollution in the next 40 years. But then in the long term, you start to get these really important and large impacts from climate, mostly heat. Heat is the biggest impact currently and projected to continue to be the biggest in the future on public health. There are other effects as well on labor and such, but the ones that are clearly documented are heat. And so these have the biggest, for agriculture, we did use precipitation and other things as well. These become important, but as I said in the beginning, it takes a while. And so this is just the final result I'll show you. This is the benefit to cost ratio. And there's 3 lines here because I've compared with different analyses of what the costs might be of transitioning to a 0 fossil fuel and 2-degree economy. If we start here, here's the one-to-one line. And so this is just looking at the impacts of climate. These are these 3. And they sort of fit the Stern Review and the OECD report and such. And they say, look, in the long run, the cost of action is less than the cost of inaction, right? So the benefit to cost ratio exceeds 1 sometime around kind of mid-century and then gets very high thereafter as the damages from climate grow. So this is really, a good thing to deal with climate change. But as we've seen all along, right, the benefit cost ratio is way less than 1 for the next couple decades. And nearly all of the spending that's involved in this transition has to take place for a couple decades, or you can't meet, say, a 2-degree target, right? You have to cut emissions by so much within the next 2 decades, it's too late to start later on. If you include air pollution, then you get these 3. And again, the spread is because there are a lot of different estimates in the literature about how much it costs to transition. But what you can see is that the benefit cost ratio, you start acting in the 2020s, and I have values for every decade. So by the end of the first decade, your benefits greatly outweigh your cost. So it's a really different perspective. It's bad that climate action yields little in the near term from climate in itself, but it's good that our benefits come quickly. When we include things like air pollution and public health, because that's what we care about, they're actually much larger than what's been in prior analysis, because there's a lot of new epidemiological studies for both heat, ozone, and air particulate. And that was the point again of the US alone scenarios, is that most of the benefits over the next couple of decades come from our actions because they're dominated by air pollution. And so this whole argument that, oh, well, climate involves a lot of spending in the near term, but we don't get anything. And, the rest of the world might not take action anyway. So is it really sensible for us to do this? The answer is really, actually, we do get a lot. We get a lot in the near term. It's just not from climate. It's from all of the co-benefits that come along from clean air. But these can be readily quantified in terms of public health, in terms of labor. We can give the results for all the different states, and we can see that they come really from our own actions. I think that's even more important in developing countries. This is a survey from the government of Chile, where they asked people about their environmental concerns. And here's a cyclist near Santiago, which is in a valley which gets lots of smog. And air pollution was number 1, but what I really like about this is street dogs were actually a higher priority than climate change for most people. And so I think in other places too, the fact that air pollution cleans up quickly and gives us enormous benefits in the near term, I think that can be really even a more compelling argument in other places than in the United States. So to close, I would say that most people around the world, their priorities are the near-term economy, it's health, it's justice. It's even if they care about the environment, it tends not to be their very top priority. So it's useful, I would say, to frame the transition to a clean economy as leading to increased productivity, especially in some of these non-traditional allies of climate action, which are the ones affected by heat, farms, construction, manufacturing, lower health and insurance premiums for all, more jobs, better health, reduced inequality. Some of those things I haven't studied, so I've given a few references, but really I think we need to convince the public that the benefits outweigh the cost, even in the near term, not only the long term. Thanks very much for your attention and for inviting me, and I'm happy to answer any questions.
Thank you, Professor Shindell. That was truly a comprehensive analysis, and it's the most comprehensive I've seen of the implications of alternative scenarios upon national outcomes of interest, ranging from, as you said, heat and mortality for air pollution. The question that I had to start out, while there are additional questions coming in from the chat, is when you describe the different RCP scenarios, at one point you alluded to the different fuel types that were included within that scenario. And I'm wondering if you could outline a path that might lead towards more rapid progression of addressing our concerns for health, for climate, perhaps some of the others that you alluded to.
Well, I think one of the things that we really need, and what just happened in Texas really showed this so profoundly, is better integration across the country and even across many jurisdictions. There's no reason that energy grids have to fit within borders. And I think that's really one of the keys to allowing greater and much faster penetration of renewables. You know, the renewables are cost effective already, and they beat any, even gas, but any fossil fuel power plant is outcompeted by renewables in many parts of the country now. But the problem is not in all parts of the country. And so you need to make sure that you can get the power to from where it's most easily produced to where it's needed. And that really requires connecting grids. Where you connect, also then, you know, you don't have to worry so much about storage, because, you know, if it's not windy somewhere, it's windy somewhere else. If it's not sunny somewhere, it's, you know, it's sunny somewhere else. And giant grids really enable renewables to penetrate much, much more quickly. I think that's really critical going forward.
Thank you. That well answers my question. For the audience, I see questions coming in from the chat, which is terrific. And I'm wondering if some of the audience members would enjoy to ask the question themselves rather than me paraphrasing them. And I see an interesting question from Aidan Lewis. If you would like to unmute yourself and go ahead, that would be terrific.
Yeah, hi, I'm Aiden, and this was just a very wide-ranging question, but what do you think the best thing that a freshman in college can do to help? What do you think the best thing is?
Oh, that's a great question, Aiden. Yeah, I'm not sure that there is a single thing I could think of, because part of the issue is that there's so much that needs to be done. And you know, we need to, of course, transition away from fossil fuels, but we need to change agricultural practices. We need to, like I was just talking about, expand the grid. I mean, there's so many practical steps on the ground. And one of the things that I would say is really challenging is the power of vested interest to outcompete the benefits of something like public health, right? Clean air or a stable climate are vast, diffuse benefits that go out to everybody. And it tends to be that if there's a small group of players that might lose $10 million by some regulation, and it might save the citizens, 300 million citizens of the US, $100 million, right? Still, the small group has a stronger voice because they're much more invested than this giant collective. So I think I think a college freshman could work specifically on environmental issues like, getting rid of fossil fuels and making sure we don't build any more, and asking their colleges to divest, and their states, local and state governments to, go for net zero carbon-free energy. Those are great. I think it's also great to really work towards an improved democratic process where there's less money from special interests that can overwhelm the will of the general public.
Thank you. I see another question, this one by John Hickey. And if you would like to also unmute, you're welcome to go ahead.
My audio is not good enough.
Your microphone is difficult to hear, so I could not comprehend that, but how about I proceed to read the question from the chat? And the question's interesting. It says that given the health impacts of air pollution, heat attack, stroke, etc., can be difficult for the general public to ascribe to air pollution versus lifestyle. How can we use the health impact as a way to motivate climate action?
Oh, that's a great question, and thank you, Randall, because I couldn't follow the out loud version either. So I think you're exactly right. You know, these are the kind of things where they're statistical deaths, and you know, for people of my generation, you know, we all had uncles that said, "Oh, you know, they say smoking's bad for you," and my friend smoked, and he's 89. You know, and like you have these anecdotal evidence that. Well, I know I never met anybody that died from this. A lot of people, of course, died from smoking, and a lot of people die from air pollution, but air pollution doesn't show up right on the death certificate. And what shows up are all the things you wrote in the chat, right? Heart attack, stroke, etc. So I think some of the things we can do that are really powerful is go beyond general numbers. And I think there's some good psychological research that shows that people care about location. And if you can give results like how many people in St. Louis, that's much more compelling to say that the leadership in St. Louis to take action. If you can also point out, which is clearly the case from research, not my own here, but lots of research, that minorities and the poor are unfairly or more sensitive and more affected by these things. You know, there's people that have the money can move to farther away from industrial facilities and farther away from roads, and they live in cleaner areas. And people have poorer air quality is a strong function of socioeconomic status, and in this country, that's a strong function of race as well. And that's really compelling to many people to show how these things are not just distributed across the population, but they're really unevenly distributed and disproportionately borne by those who are generally the least responsible. The other thing that we're working on in my group is quantifying the effects on, say, on children. And of course, that's, you know, very compelling to virtually anybody. I was going to say people with kids, but of course, it's not just people with kids, it's people without too.
Thank you. I see another question, and this person says that her microphone isn't clear, so I'll just read it off directly. And this question is about the description of a lost workday. And the question is, what is a lost workday? How is it calculated? Is it literally estimated from policies limiting working hours in high pollution or heat days? Or is it somehow estimated based off of general human physiology being proportionally lowered in a higher pollution or heat scenario?
Yeah, that's a really good question. And there's a couple ways to do this. What we're using in our work is empirical studies where people have simply tried to get data from Bureau of Labor Statistics and from employer surveys and tried to work out a relationship where you can see that at above certain thresholds, there's a certain, you know, a number of minutes per hour that a person can work decreases over time. There are others where the other area to fill in some of this information is what you're talking about is people like looking at, say, higher heat, and you see that people require a certain number of breaks that go up. And many, you know, OSHA, for example, Occupational Health and Safety in the United States requires more breaks at high temperatures. The US Army requires soldiers stationed in, you know, in the Middle East or something where it's really, really hot. They're mandatory breaks because, you know, it's very clear that the people wearing heavy clothing and doing heavy work in heat, in high heat, suffer. And so that one's really job specific, and it's mostly confined to people who cannot be in the shade, who cannot be in air condition, and who are doing something strenuous. And then there's a lot of empirical data on that. But there's some great ongoing research on how much can you cope with that by adapting, say shifting the time you work. And that's still active area of study.
Thank you. And in the essence of time, I'll ask one more question and then we can wrap it up. And this question is from Clara Goodwin, and she's asking as a future lawyer wanting to impact climate change. She's been struggling with how to integrate labor rights issues with environmental issues. And given the disproportionate impact on certain kinds of labor, do you think that there are approaches to tackling environmental issues through labor rights and safe working conditions that make more sense than others?
That's a very interesting question, Clara. Thank you. I have not thought much about that in the past, and I'm not I have no legal training whatsoever. But I do think that that's a really interesting way to go, because I talked a little bit about how there are ways to acclimatize or to adjust to some of these things, like being in the shade, or air conditioning. But when you have work environments that you can't cope with that, and when it's somebody else is forcing you to work in that case, I mentioned in response to the previous question, tobacco, and how that took a long time for people to accept these statistical deaths. But one of the first groups, of course, that made progress were flight attendants, because they were forced to breathe all this smoke as part of their job. And, they didn't smoke themselves, but the choice was taken away from them. And so that's one of the things that's quite interesting about these environmental issues, right? You don't have control over the temperature. How hot it gets during summer where you live is not really up to you if it's a function of other people burning a lot of fossil fuels and emitting CO2. So I'm afraid I don't really have a lot of good details, but I really like the way you're raising this issue, and I hadn't thought of that before. I think that's a really interesting one for those who are not able to get themselves out of harm's way. I mean, you can wear a filter for air pollution, as we've all been unfortunately doing for the last year, trying to filter what we breathe. But there's only so much you can do for heat. And if you're working outside on a farm, for example, what can you do? You can't go inside because the crops aren't inside; they're outside. So that's very, very thought-provoking. Thanks for the question.
Well, thank you, Professor Shindell, for that fascinating presentation, for the interesting question and answer period, and for, in general, sharing your wisdom with us. We greatly appreciate it.
Thank you for having me.
The pleasure is ours, so thank you. And this will conclude our program, and I'd encourage all of the audience members to go to the Climate Change Program website for future events. Thank you, everyone. Have a great evening. Bye.
Thank you.
Thanks, Randall.
Thank you, Drew.